All right, so far we've talked about two-dimensional vectors, then we moved on to three-dimensional vectors, and now we're going to start working with vectors and doing some operations on vectors beyond the easy add, subtract, and stretch kind of things. And one of the things we said before is if you want to multiply vectors, you really can't. Well, I kind of lied a little bit because we did kind of multiply a vector, except we multiplied a vector by a scalar. Another way of sort of kind of not really multiplying vectors is to find what we call the dot product of two vectors. And believe it or not, this name comes from the fact that if you take a dot, isn't that an indication that you are multiplying? It is, and I don't know this 100% for fact, but I am really, really sure that what happened is people were trying to decide on names for this stuff. They said, well, let's just call this the dot product because we're kind of multiplying vectors here. So that's why it's called the dot product, because we're actually kind of multiplying vectors here. So what is this dot product that I speak of? Well, simply put, the dot product of two vectors is the sum of the products of the respective components of the vectors. All right, so what does that mean? Let's say I have a vector in the plane, u1, u2, and another vector, v1, v2. The dot product, u dot v, is when you take u1 times v1 and then add it to u2 times v2. u1 v1 plus u2 v2. If you have a three-dimensional vector, same idea, only you just go a little bit further and do it 3 times, okay? Now, the question I always get is, does the dot product yield a vector? Is it a scalar? I mean, you said we can't multiply vectors. Well, you can't really multiply vectors, but we kind of sort of multiplied their components and then added them together. Well, if I add things together, notice nothing is bold on this side. Number plus a number plus a number is going to give me another number. So the dot product gives you a scalar in this case. Now, strictly speaking, the dot product does not have any visual meaning. You can't say, well, what does that look like? Well, it doesn't really look at anything. It gives us a value, and that value is indicative of a couple different things that we'll get to. But in and of itself, if I say the dot product of these two vectors is 17, you could say, okay, good for you. However, it is used a lot, so we give it a name and we use it as an operator. Okay, it's an operation on vectors that we use often enough to give it a name. All right, so let's get into it. Properties of the dot product. Well, the dot product is commutative. U dotted with v is equal to v dotted with u. Also, u dotted with the sum of two vectors is equal to the sum of the dots. If you want to do a dot product and multiply by a scalar, you can kind of sort of distribute that scalar to either one of the dot products. We don't use that too often. If you dot the 0 vector, notice how the 0 is bold. If you dot product the 0 vector with anything, you get 0. And if you dot product something with itself, you get the square of the magnitude of those vectors. Because if you think about it, when you do v dot v, it's v1 times v1, which is v1 squared, which is part of the formula for a magnitude. All right, so let's say I have vectors 2, -2, 5, and 4, 8, -7. We're going to calculate some dot products here. So if I have u dot w, that means I'm going to do 2 times 4 plus -2 times 8 plus 5 times -7. Okay. So if I do that, 2 times 4, -2 times 8, and I do that, I have 8 minus 16 minus 35, which is going to be -43. Okay? There you go. There's the answer. What does it mean? I don't know. Well, I do know, but you don't know yet. What if we did u dot u? Well, u dot u would be 2 times 2, which is 4, plus -2 times -2, also 4, plus 5 times 5, which is 25. So I have 25 and 8, 33. U dot w parentheses u. So you have to read this carefully. So u dot w is going to give you a number, and now I'm telling you to multiply a number by a vector. Can we do that? Yeah, it's like multiplying a constant by a vector. No big deal. So u dot w we had from over here, that's -43, and then we're supposed to multiply that by u. So we're going to take -43 and multiply by 2, -2, and 5. So that is going to give me, let's see, 2 times negative 43 is negative 86. Negative 2 times negative 43 is going to be positive 86. And 5 times 43 is going to be 215, if I'm not mistaken. And so now I got a vector, because I took a dot, and then I multiplied a dot by a vector, which will give me another vector. All right, u dotted with 2w. So you can do a couple different things. U dotted with 2w uses this idea right up here, where you can multiply that 2 kind of whenever you want, when you're done in with u or in with v. So if I want u dot 2w, I'm looking up here and I'm like, wait a minute, I have u dot w already. So that's the same as 2 times u dot w. And that is going to give me 2 times negative 43, which is negative 86. The magnitude of u dot w, wait a minute. You can't take the magnitude of a scalar. That doesn't make any sense. This is nonsensical. Is that how you spell nonsensical? Nonsensical, L-E? I don't know. Let's just write, can't do it. When in doubt, use a different word. We can't do that. You can't find the magnitude of the scalar. Doesn't make sense. There may be some people who argue with me and say the magnitude of negative 43 is positive 43, and I go with that argument, but these double bars really mean find the magnitude of the vector inside, and if there is no vector inside, you can't do anything. What about u dot w dot u? Can I do negative 43 dotted with u? Can I dot a scalar with a vector? No, I cannot. I cannot do that. So this also is a can't do it situation. Again, I may have people argue with me and say, well, wait a minute. If this is just a dot and it's really a times sign, can't you just multiply negative 43 times u? No. I would argue back that you cannot do that, because if this is one operator meaning a dot, then this operator has to mean dot also, which means we're implying vectors. And if I don't have vectors, I'm done. So can't do that one, can't do the other one. All right, so why do we care? What's one reason we use these dot products? Well, because we like to use dot products to help us calculate angles. Angles are very important, and we need them. So the most important use of the dot product of two vectors is that it allows us to calculate the angle between two non-zero vectors. Fantastic. Here's the rule. The rule is cos theta equals u dot v over the magnitude of u times the magnitude of v. So it's the dot product divided by the magnitudes of the individual vectors. That gets you the cosine of the angle between them. Now, one thing that's important here is in order for this to work, your vectors have to have the same initial point for this to work appropriately. If they don't have the same initial point, you will get the supplement of the real angle. So what does that mean? What it means is let's say I have A, B, C, okay? If I do AB dot AC over the magnitude of AB, BC, this will get me the cosine of A, okay? A to C, A to B, they have the same initial points. If, however, I did not follow the rule I just put in place and said, what if this instead, oh, I wrote BC, I meant AC down here. What if this instead said AB dot CA? Well, if that happens, you're going to end up with a negative up here, because the problem is you now have this vector times the negation of another vector, and you're going to end up with the supplement of what you wanted. So especially if you have a triangle where everybody's connected and you know that there are initial and terminal points that are important, in order to use this formula, you have to use two vectors with the same initial point on top. Okay? All right, so here is where you're going to love me. We're going to prove it. Where did they come from? Where did it come from? Well, you know where it came from? It came from the law of cosines. So let's talk about the law of cosines. Do you remember the law of cosines? I remember the law of cosines. The law of cosines says the following. C squared equals A squared plus B squared minus 2AB cosine C. All right, well, if I want to do this and I want to work with vectors, A, B, and C are the lengths of the sides. And if I look at the triangle given here, the length of this side is the magnitude of V. The length of this side is the magnitude of U, and the length of this side is the magnitude of V minus U. Oh yeah, remember that from before? When you have the third side of a triangle, it's actually the difference of the two vectors. Remember that from before? So, if I take C squared in this diagram, that would be the magnitude of V minus U squared. And this would be U squared. And this would be V squared. Oops, not plus, minus. Minus 2 U V cos theta. So I just rewrote that formula using the diagram given. Okay, fine. Now, what am I going to do next? Well, what I'm going to do next is I'm going to come over here and say, well, what if I called U, U1, U2, U3, and I call V, V1, V2, and V3. That means the vector V minus U would be V1 minus U1, V2 minus U2, V3 minus U3. So then, when I come up here, V minus U squared really would be the magnitude which has a square root on it, right? Think about the square root you get from a magnitude here. If I take the square root and then square it, you know how they kind of cancel out? So if I have V minus U squared, really that just gives me the sum of the squares of V minus U. So this is going to be V1 minus U1 squared plus V2 minus U2 squared plus V3 minus U3 squared equals U squared, so U1 squared plus U2 squared plus U3 squared plus my baloney has a first name, it's O-S-C-A-R. My baloney has a second name, it's M-A-Y-E-R. 'Cause Oscar Mayer has a ring, B-O-L-O-G-N-A. Okay, so there we go. This kind of continues on here. This is a minus, and then it scoots down here, minus 2uv cos theta. Now, I could have written this part with the square roots on it. I don't want to. Trust me, you don't either, because it's just going to go back to this way anyway, so just leave that for now. So, I've got this. Wow, okay, well, what's my goal here? I want to use the law of cosines to prove this formula up here. So I want to get cos theta alone. So if I want to get cos theta alone, I'm going to swing all of this over to here and take all of this stuff and move it over to here. So I'm going to have 2 u v cos theta equals u1 squared plus u2 squared plus u3 squared plus v1 squared. I know you're loving this. So I had all of this, and then I moved this left side over to the right, so I'm really subtracting all of that stuff now. So it's minus v1 minus u1 squared minus v2 minus u2 squared minus v3 minus u3 squared. Okay, I know you're loving this. I know you want to quit and you want to say, dear God, when is she ever going to finish this? I promise it's coming. So I have 2 u v cos theta equals. Now watch this. On top, I'm just going to do da-da-da-da-da-da-da. This is all the u's and v's on this top row. This second row that is in this blue box right now, I'm going to distribute it. So if I did v1 minus u1 squared, that would be v1 squared minus 2u1 v1 plus u1 squared. Think about what happens when you FOIL this. So my top row stays the same, but now my bottom row is going to be minus v1 squared plus 2u1 v1 minus u1 squared minus v2 squared plus 2u2 v2 minus u2 squared minus v3 squared plus 2 u3 v3 minus u3 squared. And now, if I put this stuff back on top, I'm going to make it a different color. The top stuff was u1 squared plus u2 squared plus u3 squared plus... I know, I'm bored of writing too. So if I take this now, I have a u1 squared up here, I have a u1 squared down there, and it's negated. Gone. u2 squared, negative u2 squared, u3 squared, negative u3, v. Oh my goodness, I'm running out of room. So, on the left, I still have 2 magnitude of u, magnitude of v, cosine theta, and on the right, I have 2 u1 v1 plus 2 u2 v2 plus 2 u3 v3, and that's it. That's all I have left. If I divide both sides by 2, these guys drop. If I divide by these magnitudes, I get cos theta equals, well, wait a minute, u1 v1, u2 v2, u3 v3, isn't that u dot v? And on the bottom, I have the magnitude of u and the magnitude of v. Whew! All right. Do you have to memorize that? No. Did you have to understand what I did? Yes. Yes, yes, absolutely yes. You had to at least be able to follow that. And one of the things that I also wanted you to get from that is when you look at it, notice the dot product didn't show up in the proof. What historically happens in cases like this is mathematicians, they go through, they prove a bunch of stuff, and they see these same things coming up over and over again. In this case, what they saw coming up over and over again is they kept seeing things where you had u1 v2, u1 v1, u2 v2, and u3 v3. They kept showing up over and over again in these proofs that they did. So they said, well, let's stop calling it that and just start calling it u dot v so we don't have to write all this stuff out every time. So that's kind of how the dot product evolved. It's not like somebody said, let's name the dot product. It's that somebody said, wow, this happens a lot. Let's call it something so it's an operator that we can anticipate. Okay? Now, after that, we should actually probably, be able to use it. So let's say I have vector u, v, and w. Find the angle between. Now, for a second, you might go, wait. Didn't we just say on the last slide, if I want to find the angle between them, I need to know they have the same initial point? Yes, that's true if you start with points. If you are just given vectors like we're given here, you can assume that when you find the angle that you are finding the angle between the initial points, or that whether you get the supplement, or the angle itself, either are helpful. Okay? If you are given coordinate points and told to find the angles between, say, points on a triangle, then that initial point condition really matters. Okay? So here's some vectors. I can just assume they have the same initial point. I want to find the angle between each indicated pair of vectors. So, long story short, we did all that before to say that cos theta equals a dot b over the magnitude of a times the magnitude of b. So if I want u and v and I want to find the angle between them, cos theta is going to equal u dot v over the magnitude of u times the magnitude of v. And however much work you want to show for this, I can live with. Show enough work that you know what you're doing and that you don't make a mistake. So, cos theta equals 3 times negative 4, which is negative 12, plus 1 times 0, which is 0, plus negative 2 times 2, which is negative 4, over the square root of 9, 10, 14, and the square root of 20. So that's going to give me negative 16 over the square root of 14 times 20. So in my calculator, I'm going to here and do negative 16. Hello. Slow calculator. There we go. Negative 16 divided by the square root of 14 times 20. And I am going to take the inverse cosine. Let's see, I am in degree mode. You can be in degree or radians for this. I can live with it. Just give answers that I ask for. So if I ask for radians, give me radians. If I ask for degrees, give me degrees. If I don't tell you what I'm asking for, whatever one you give me is fine. And 162.976, I'm going to call that 163 degrees. That is the angle between the vectors. So if you're feeling good, I want you to pause it, do the other ones on your own, and then come back and check your work. If you paused and came back, you should have gotten 17, 90, and 180. The bottom two were special. The 17, piece of cake, you follow through as normal. C, though, on top you get a 0. So cos theta equals 0. What's the inverse cosine of 0? Well, 90. Now, when we do inverse cos, technically, yes, there's an infinite number of answers, but we're only interested in the primary answer, okay? And then when we did D, you ended up with cos theta equals negative 1. The inverse cos of negative 1 is 180. And if you look at V and Z, you will notice that they are parallel, but pointing in opposite directions. So V looks something like this, and Z looks something like that. So the angle between them will be a nice 180. Okay. What does it happen? What does it mean? We just talked about that. What you should definitely know, though, is if the dot product of two vectors is 0, then the vectors are perpendicular, and we also call them orthogonal. Orthogonal. Do you remember from geometry there was that orthocenter when you found the point of intersection of the altitude of the triangle? Those were called the orthocenter. Had the same prefix there. Remember, your orthocenter came from altitudes, which are perpendicular to the sides. Now we're using perpendicular and orthogonal together. So you may notice that prefix as you move further and further in that. It's one that pops up a bit. So, dot product equals 0. You know the two things are perpendicular to each other. You know that the vectors are orthogonal. All right, points A, B, and C create a triangle in space. Find the measures of the three angles of the triangle and classify it. So this is a case where that beginning point matters. So if I have A, B, and C, I need to take that triangle and make vectors out of the sides. So if I want to find angle A, I need to use AB and AC. So AB is 3, 5, negative 8, and AC is 0, 5, negative 12. So if I want cos A, I have to do AB dotted with AC over the magnitude of AB, AC. So AB dot AC is going to be 0 plus 25 plus 96. And my magnitudes are going to be the square root of 9 plus 25 plus 64. And the square root of 5 squared, which is 25, and 12 squared, which is 144. So inverse cosine of 25 plus the 96 divided by the square root of 9 plus 25 plus 64. And then that is being multiplied by the square root of 13. So I'm just going to put divided by 13. That'll do it. Ignore my messy calculator tactics, I promise. They're legit. 19.91, so we'll say 19.9 degrees. And then if I want cosine B, that's going to be BC, BA, and the magnitude of BC and BA. All right, so I have AB, which means I really also have BA, don't I? Because I can just negate this. I don't have BC yet, so let me write that one down. BC is, let's see, down 3, 0, and down 4. So if I do BC dotted with BA, basically I'm going to multiply these and then negate it, because BA would be a negative 3. So negative 3 times 3 is negative 9, make it a positive. 0 times that is 0. And negative 4 times negative 8 is positive 32, but I'm going to negate it and make negative 32. Whoops. And then on the bottom I have the magnitude of BC, which is the square root of 3 squared plus 4 squared, which is 5. And then I have the magnitude of BA, which, let me just try and add it now. I've got 64 and 25 is 89, plus 9 more is 98. So I have 9 minus 32, which is negative 23, over 5 times 98, which is negative 23 divided by 5 times 98. 92.69, so we'll say 92.7. Now, yes, you can take the shortcut and say, I have two angles of the triangle, can't I just subtract from 180 to find the third? Absolutely, but I really suggest calculating it and then checking to make sure they add to 180. That way you give yourself a second backup check. So really quick, cos C is going to be CA times CB, which is the same as, or I shouldn't say times, CA dot CB, which is really the same as AC dot BC, because the C's are both at the end, and you negate the negative, and you end up back where you started. So for cosine C, I'm really just dotting these two things right here, which is going to be 0, 0, and 48. And then on the bottom, I have the magnitude of AC, which is the square root of 169, and the magnitude of that, which is the square root of 25. So I really have 48 over 5 times 13. Did I do something wrong here? Wait a minute. I did. The magnitude of BA isn't 98. It's the square root of 98. Dang it. See, look. Another good reason to check your work. You probably have been yelling about that at home for a couple minutes. Sorry. Let's fix it. Let's see. Second enter. Let me slap a square root on this guy. All right, 117.7. We'll see if I'm right. Sorry about the mistake. It's going to happen. Sometimes I make mistakes and I delete them out of these videos. Other times you just have to sit at home probably screaming to yourself until I fix it. If you ever see a mistake in one of my videos and I don't fix it, please, please, please let me know as soon as possible so I can fix it, okay? Okay. But this is definitely a 5 and a regular 13, so that I know I'm covered. And so I have the inverse cos of 48 divided by 65. 42.4. All right, now let's check here. So I have 42.4, 117.7, and 19.9. 180. Woo! See, look at that. I caught my mistake, and it worked out. Ta-da! All right, so here's my three angles. Classify it. Well, it's going to be obtuse, and I can also tell right now that it is scalene. There you go. Okay, it has been 30 long minutes, so I am sorry for the length of this video. So a quick joke, and then you are on your way. Quick joke for the day. What's brown and smells like a bell? My son would love this. What's brown and sounds like a bell? Dung. I know it's terrible, but it's a joke that has to do with poop. And I have a 6-year-old boy. They like poop. All right, other one, not so gross. Why did the banker break up with his girlfriend? He just lost interest. Okay, goodbye. I'll let you go, and let me know if you have questions or if I made any other mistakes.